Congruent number problem is one of those deceptively simple problems in number theory that is incredibly easy to state, but still remains unsolved to this day. The problem was considered since at least the time of Fermat, and probably even earlier. The congruent number problem simply asks which rational numbers can be expressed as the area of some right triangle, all of whose side lengths are rational numbers. So for example, we can see that 6 is a congruent number because it's the area of a 3, 4, 5 right triangle. And similarly, this more complicated triangle has area 5. So 5 is a congruent number. We can convert this geometric idea into more number theoretic terms by using the Pythagorean theorem and the formula for the area of a right triangle. So we see that a rational number n is only congruent if there are 3 other rational numbers a, b, and c that satisfy these two Diophantine equations. At this point we can make a simplification. By scaling all of the sides of the triangle, multiplying a, b, and c all by a constant factor s, we see that if n is congruent, then so is n times s squared. So this means that we only have to consider square-free integers when solving the congruent number problem. To consider any other rational number, we only have to look at its square-free parts to determine whether or not it's congruent. One way that one might try to go about looking for congruent numbers is to list out all of the primitive Pythagorean triples and then calculating congruent numbers from that. The problem with this is that there's no real discernible order in which the congruent numbers appear, so it's impossible with this method to prove that a number isn't congruent, and for this we need some more sophisticated techniques.
So the first step to approaching the congruent number problem is to prove that 1 is not congruent, and by extension that all perfect squares are also non-congruent. We know that these two are connected because if we were to assume that there is a rational right triangle with area 1, then we could achieve any other area of a perfect square just by multiplying the side by some sort of rational number, by some sort of integer, which would make the area into this integer squared times 1, and that means that the area would be this integer, and since this first triangle that we created with area 1 does not exist, it means that all the subsequent triangles of like k squared area do not exist. Like for example, let's just say we had a, b, and c arbitrary numbers, and their area, which is an important number, area is equal to 1. We can create any other triangle with area of a perfect square. We're multiplying these by, let's say, some sort of factor k, ak, bk, ck. Our area would become 1 times k squared, and since k can be any integer, that means that any perfect square is not going to be a congruent number. Right, so the proof used to prove that 1 is not congruent is called Fermat's theory of infinite descent. And what this theory basically says is that if you can create a set of solutions that will necessarily create another smaller set of solutions, then this smaller set of solutions will create an even smaller set, which will in turn create another even smaller set, and a fourth set, fifth set, sixth set. It's an infinitely descending set of solutions since they're all decreasing from each other. And this is impossible because of the well-ordering principle, or also known as the least integer principle, which tells us that there has to be a least solution that exists. And if there's an infinitely descending set of solutions, then that means the original assumption that we operated under when getting our first solution, that assumption was incorrect. And the assumption that we're going to be operating under is that 1 is a congruent number, and after we find that there is an infinitely descending number of solutions, we can assume that our assumption is incorrect and 1 is actually not congruent. So let's first set up our assumption, which is that 1 is congruent and is an area of a rational right triangle. So we'll make this A over D, B over D, C over D. The reason why we have this over D is because A, B, and C are integers, and we'll make some sort of area, but we need an area equal what? So let's just assume that this area created will be D squared, and this factor D will modify the area, make the area what? Here's the important part. Now, Fermat's theory of infinite descent has a long proof that takes about 15 minutes to write down, probably 15 more minutes to properly explain. So we'll be laying down the framework and the bare bones. We just need to know that it works and it proves that 1 and all these other perfect squares are not congruent. So the equation that we need are a squared plus b squared equal to c squared. Standard Pythagorean theorem. We do a over d squared, b over d squared equals c over d squared. I mean, since they're all d squared, you can just factor it out. And then we also need our area equation. So we get 1/2 times a over d times b over d. So we get a 1, and this is more conveniently written as ab equals 2d squared. Now, these two equations that we just wrote down, these two equations together, will allow us, after a lot of algebra, it will allow us to create another set of solutions. A prime, B prime, C prime, and D prime. After we go through the proof, we will have seen that A prime is less than A, B prime is less than B, C prime is less than C, and D prime is less than D. But they are all greater than 0. So we know that these are descending solutions. And we also know that using this new set of like these prime solutions that we call them, these prime solutions, we can create even more solutions like A double prime, B double prime, C double prime, D double prime, triple prime, quadruple prime. So in effect, we have just created an infinitely cascading, infinitely descending number of solutions, and thanks to the well ordering or the least integer principle, we know that this is impossible. So we know that the original assumption that we operated under is incorrect. And our original assumption was that there exists a triangle with area, a rational right triangle with area 1. We know that this assumption is now incorrect. Now, it's important to note that this big proof, it only proves that 1 is not congruent and that perfect square is not congruent. If we were to still pick up any rational number off the street, or we would just pick any rational number at random, we would not be able to use this to prove its congruency unless it were a perfect square. So in order to do further analysis to the congruent number problems, we look to elliptic curves.
So it turns out that there is a one-to-one correspondence between right triangles of rational side length with a given area and non-trivial rational solutions to an associated elliptic curve. You can check for yourself that the formulas I've given here define a bijection. However, where it really gets interesting is when you're able to apply the algebraic structure of the elliptic curve to rational triangles. So for example, because there's a well-defined notion of adding 2 points on an elliptic curve, you're able to take a single rational triangle and add it to itself multiple times to show that given just one rational triangle of area n, there are infinitely many rational triangles of area n. Here we can see a specific example. The 3, 4, 5 triangle, which has area 6, corresponds to the points 12, 36 on the corresponding elliptic curve. And when you double this point, you get the points 25 over 4, 35 over 8, which gives you this new right triangle completely distinct from the previous one, but that also has area 6. In fact, elliptic curves have brought us pretty close to a near complete characterization of all congruent numbers. In 1983, Gerald's tunnel was able to prove that, assuming the as of yet unsolved Birkin-Swinerton-Dyer conjecture holds, then whether or not a number is congruent depends entirely upon the number of solutions of a couple of simple Diophantine equations, allowing us to determine whether a number is congruent with a finite number of calculations.